In this lesson, we're going to learn how to construct confidence intervals for the mean when we know sigma. And if you remember, sigma is a standard deviation that comes from the population, not from the sample. And when we do statistics, what we want to do is come up with a question. We collect data to answer the question, describe the data, and draw conclusions. And now I'm going to talk to you about how to make a confidence interval, which is one of the most commonly used methods for drawing conclusions. And I want you to look at this question. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to the teaching of reading. At the end of the program, the students will be given a standardized reading test. Suppose that the mean score for the 100 students is 67.30. This is your sample mean, X bar. Now, the administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. So what they want to know is if I switch to this reading program, what's going to happen next year for everyone? What's mu going to be? The true population mean. Right now, the best estimate for the population mean, mu, is the sample mean, X bar equals 67.30. This is called a point estimate. All right, but now here's what's going to happen. It's very unlikely that X bar equals 67.3 is exactly equal to mu, what's going to happen next year. In order for the estimates to be useful, we must first describe how close it is likely to be. For example, if I think it could be off by, say, 10 points, we would estimate mu with the interval 67.30 minus 10 is 57.30, and 67.30 plus 10 is 77.30. And if you look at this, this is how Alex does the mu. That's how you're going to type it in on, does the confidence interval. That's how you'll type it in on Alex. This could also be written as 67.30 plus or minus 10. The plus or minus number is called the margin of error. And the interval used to estimate the value of the parameter is called the confidence interval. And if you look at this picture, I've got 67.30. I add 10, I get 77.30. I subtract 10, I get 57.30. Suppose that we require a certain level of confidence, say 95%, that the interval contains mu. The real question is, what should the margin of error be in order to have 95% confidence that the population mean is in the interval? And what that's going to get into is your familiar z-scores that we did before. The margin of error for any level of confidence can be found using the sampling distribution of X bar. We begin by finding the margin of error for a 95% confidence level, and then we'll keep going from there. But before we do this, I want you to get back up here, and I want you to look at the 67.30 plus 10. I want you to look right here. This is how I usually do the confidence interval because I think it's easier. I say 67.30 minus 10 is 57.30. And 67.30 plus 10 is 77.30. And that's the same thing as what we did up at the top with the less than mu and the less than. Two different notations for a confidence interval. Now, we know how to find this z. It's the same z that we did back in chapter 7. When you're doing this, what you're going to do, recall the previous technique used to find z-scores. You don't need to find the right tail and the left tail. All you need is the center. And what I'm going to do, I'm going to go to my calculator. You all saw how I closed out the calculator. That resets everything. I don't know if you can do that on your phone or not, but it saves you having to clear everything. And what I'm going to do is I'm going to go to distribution, and I'm going to go to normal. Anytime you want a z, the mean is 0, the standard deviation is 1. And I want a center curve. And I want my area to be 0.95. And if you look, the calculator gives you the two z-scores. The first one is a negative 1.96. The second one is a 1.96. What that's saying is 95% of the area is bounded within 1.96 standard deviations. 1.96 is called the critical value. And like I said, it's what we already know from chapter 7. Now, when the sample size is large, the CLT tells us that the sampling distribution is approximately normal with mean of mu and standard error of sigma of x bar. Remember what I made you write in 7.3. Because the sampling distribution of x bar is normal, 95% of the sample means will lie within 1.96 standard deviations of mu. In general, the margin of error is going to be in this form. It's going to be the critical value times the standard error. The critical value is the z. The standard error comes from the formula. So that's what we're going to do. The standard error is at sigma of x bar. For the new example on the approach to reading, suppose that we know from past results that scores on the standardized reading test have a population standard deviation of 15. Now this is sigma. The standard error is sigma of x bar equals sigma over root n equals 15 over our sample of root 100 equals 15 divided by 10 equals 1.5. The margin of error is the critical value times the standard error. 1.96 times 1.5, which is 2.94. And what Alex does is it makes the confidence interval like this. It says, okay, let's do x bar minus 2.94 is less than mu is less than x bar plus 2.94. Then it puts the x bars in. Go to your calculator and just do that arithmetic. I've got 67.30 minus 2.94. Oh, hold on, I'm in the wrong place. Go to calculation. And I do 67.30 minus 2.94. All right, and I get 64.36. And I do 67.30 plus 2.94. And I get 70.24. Now, what I do for this that I think is easier is I start with when you do your confidence interval, you're going to end up here with your math. You're going to have 67.30 plus or minus 2.94. Alex is going to go to this. What I do is I just do 67.30 minus 2.94. You always want to subtract first because you want your smallest number first, your smallest bound, 64.36. And then I do 67.30 plus 2.94. And I get that same thing, 70.24. And we are 95% confident that the population mean score on the standardized reading test is between 64.36 and 70.24. So this is what I think is going to happen next year. I think they're going to score, mu is going to be between these two numbers. That's what I think. And for example, if mu is 65, my confidence level is good because 65 is in that confidence, and my confidence interval is good because 65 is in that interval. If mu is 80, my confidence interval did not work. It did not contain mu. If mu is 50, my confidence interval did not work. It did not contain mu. And we'll get into that more later too. Now this next page is going to be a lot of definitions. And I want to start with some definitions from our first chapter. When we have a parameter is coming from the population. And when we have a statistic, it is coming from the sample. And Right now, a point estimate is a single number used to estimate the value of an unknown parameter. All right, I always want to estimate mu. Now, what the confidence interval is it's an interval that is used to estimate the value of a parameter. And what the confidence level is, that goes along with the interval. It's a percentage between 0 and 100 that measures the success rate of the method used to construct the confidence interval. And what the margin of error is it's the plus or minus number. It's your wiggle room, how much you're willing to be off. The plus or minus number. The margin of error equals the critical value that comes from the curve, the z-score, times the standard error. And the standard error is sigma of x bar. It's sigma over root n. Now let's talk about this confidence level again. Say that we all made confidence intervals and we took samples of 50 males at SU and found their average height. And we made intervals that were at a 99% confidence level. So we all made 99% confidence intervals, all of my students and me. Now here's what happens. If we draw many samples, and use each one to construct a confidence interval. Um, 99% of them will contain the true population parameter, the true mean. 1% of them will be wrong. They will not contain mu. And it's not anything that you did wrong. It's just chance. So it's just chance in that sample. What I want to talk about here are the critical values that go along with the confidence intervals. And they get the critical values from the table. You all know we're not going to use the table, but what I want you to note is just it's still a Z. It's a Z score, but the only difference is now they give 3 decimal places. Now, I want you to look at this problem. It says a large sample. They're saying that so they know you can, you can use the normal curve, CLT. Has mean of 7.1 and standard error of 2.3. They're giving you the standard error. Construct a 90% confidence interval for mu. Now, what the margin of error is, it is the critical value times the standard error. All right, and if you look in the chart, it gives you the critical value for 95%, but I want to show you how they get that because we're not going to use the table. So now for this one, for this problem, I want a 90%. So for this problem, I want to show you how they get this 90%. All I do is go to my center curve, 90%, and I go out to my distribution. Always go back and make sure your parameters are correct. They are. It is a center tail, and I want the area to be 0.90. Now notice we want 3 decimals. This gives you 2 scores. It gives you 2 z-scores. It gives you a negative and a positive. So the negative is negative 1.645 and the positive is 1.645. You're going to always use the positive, and I'll explain why in a minute, but you want to use the positive. Now, here's my margin of error. It's my critical value, 1.645, times my standard error, 2.3. All right, so I'm going to go out to just regular math, and I'm going to do 1.645 times 2.3. Now, if you see these decimals, typically we keep all the decimals. Just to make this easy, I want you to put 3.8, just to make this one quick to type in. Now, here's what I'm going to do. Here's what Alex does. It says, okay, x bar minus 3.8 is less than mu is less than x bar plus 3.8. X bar is 7.1. All right, so I'm going to do 7.1 minus 3.8 is 3.3 is less than mu is less than 7.1 plus 3.8, 10.9. Now, I'm going to show you something I like better. When you're doing the confidence interval, you're going to get to here, 7.1 plus or minus. This is what I showed you on the last one, 3.8. Now, here's what I do. You always want the smallest number first. So you're going to do 7.1 minus 3.8, 3.3. 7.1 plus 3.8, 10.9. But both ways are fine. Alex does what's written in blue. Now, the next thing I want to talk about is something called Z alpha notation. And I want you to draw a couple of these alphas. And all it is a z-score. We've already done them, but it's a new notation so that you know that it's a critical value. And if you look at the notation, it's z of alpha over 2 and negative z of alpha over 2. And you all, I told you we always pick the plus, the positive instead of the negative. That's because when we get here, you're always doing plus minus, so you don't want to get into a double negative. All right, now back to this. I want a critical value. Z of alpha over 2 is a critical value for 92% confidence. Now, Z of alpha over 2, like I said, is a critical value. Now, here's what I want. I want the middle curve, the center tail, to be 0.92. And I'm going to get a negative Z of alpha over 2 and a positive Z of alpha over 2. And go to your calculator. I'm going to go to distributions. This is fine. So I'm going to go to a center tail. And I want my area to be 0.92. All right, so my 2 z-scores are my notice I called it a z-score. Same thing. It's a critical value. It's negative 1.751 and positive 1.751. Now, a notation that I like better is I like z of alpha over 2, but I like to save alpha for chapter 9. So the notation I like is z star. And this is the critical value. And what Z star is for this problem, I'm going to take that positive one. It's 1.751. Now, here's what we're going to get into in the next lesson, 8.2. What we just did describes constructing a confidence interval for a population mean, and it requires us to know sigma. Now, the advantage is we kept doing stuff with Z all day. So we were doing everything we did in chapter 7. In practice, sigma is usually not known. And that is what we'll get into next, what to do. Now, we're going to do a confidence interval at the end, but what you're going to do is check your assumptions before you get started. And you can call them assumptions or conditions. And here's what needs to happen. First of all, you need to have a simple random sample. All right. And second of all, either the sample size is large greater than 30, so CLT holds, or the population is approximately normal. And what I'm going to show you in the next thing, we're going to do a full confidence interval for this problem. This is the same problem that we've been looking at, and it's a different confidence level. And I'm going to show you how to do a full construction of a confidence interval on this. Now, when you look at it, notice that I have sigma. So I'm given population standard deviation. I'm going to do a one sample Z interval. And what you're going to do first is you're going to check your conditions or assumptions. You don't have to call it both things because that is redundant. But here's what I'm going to do. The first thing I'm going to say, we did a simple random sample, check. The second thing I'm going to say is you want to check that normal condition. If the problem said anything about normal, you're going to say normal population. It didn't, but I've got a sample of 100. So what I'm going to say is N is greater than 30. So the central limit theorem tells us that our sampling distribution is approximately normal. And you all saw what I'm going to write out for that. All right, so the first part of a confidence interval is your conditions. The second part is your math, and I'll do the math in red. The math, the confidence interval, is your point estimate plus or minus margin of error. Now, I usually don't write this, but I write it with the formula. So here's the formula. The point estimate is X bar. The margin of error is our critical value, Z star, times our standard error, sigma over root N. All right, and the first thing I want to do is get Z star. So I want 98% confidence. I'm going to go to my calculator. Always go back and make sure that you're good, and I am. And I'm going to do a center curve. And I want the area to be 0.98. So my Z star is going to be, I want 3 decimals, 2.326. Now, the next thing you're going to do is you're going to substitute in your variables. So my X bar is 67.30. My Z star is 2.326. My sigma is 15. And my N is 100. Now, this part of the formula is the margin of error. You always want to keep that separate. So here's what I'm going to write next. I'm going to write 67.30 plus or minus, and go to your calculator and you can type that all in at once, the margin of error part. So I'm going to say 2.326 times the quantity, 15 divided by root 100. All right, and I get 3.489. And you want to leave 3 or 4 decimals. And obviously that's 3. So I'm going to leave 3 decimals. And then I'm going to do 67.30 minus 3.489, 63.811. And I'm going to do 67.30 plus 3.489. And I get 70.789. And that's my confidence interval. Now, what we're going to say next, to give your conclusion, that's going to be the last part. When you give your conclusion, you don't want to talk about the sample. I don't care about the sample. I care about mu. So here's what we're going to say for the conclusion. I'm going to say we are 98% confident that the true population mean, that you always want to talk about true population mean, nothing about sample. Then you want to talk about the problem. So the true population mean test score is between 63.811 and 70.789. Now, you will get questions like this. So you will say, someone says the test score will be 70 next year. Does your interval support that? And you're going to be real basic in your explanation. You're going to say, yes, 70 is in my 98% confidence interval. Someone might say, I think the test score next year is going to be 60. Does your interval support that? And you're going to say, no, 60 is not in my 98% confidence interval. All right, so that's the end of confidence intervals for the mean when we know sigma.